Let's start with chapter 11, thermal energy and transfers. Our first concept is about conduction, good and poor thermal conductors. Good thermal conductors are solid that allow heat to move through them easily, such as aluminium, cookware, or copper wires. Poor conductors are insulators. They do not transfer heat efficiently like wool blankets, cardboard, or paper. Why tiles feel colder than carpets? This comparison shows why houses often use carpets or rugs. Method: use an area of bare tiles or stone floor. In the same room, place a thick rug or towel on the floor for several hours so both surfaces reach the same temperature, which is thermal equilibrium. Stand with the bare feet on one foot on tile and one on the rug. Compare how warm or cold they feel. Observation: the tiles feel colder while the rugs feel warmer, even though both surfaces are at the same temperature. Explanation: tiles and stones are good conductors. Heat flows quickly from your warm foot into the tiles, causing your foot to lose energy and feel cold. Rugs and textiles are good insulators. They do not let heat escape quickly, so your foot stay warmer. Wood versus metal conduction test. Burning paper experiment. A rod made from half wood and half metal is wrapped tightly with paper. Method: hold the rod above a gentle flame and heat the section where metal and wood meet. Rotate the rod so all parts of the paper heat evenly. When the paper is discolored, remove it and examine the burn marks. Observation: paper touching the metal remains undamaged. Paper touching the wood becomes charred. Explanation: metal conductors heat well, so heat travels away from the paper into the metal, preventing burning. Wood is poor conductor, so heat stays in the paper and burns it. Comparing conductivity of different metals. Four metal strips of identical size are attached to a central insulated block. Small ball bearings are fixed to each strip with wax. Method: heat the center where the strips join. As heat travels along each strip, the wax melts and ball bearings drop. The strip where the ball bearings falls first is the first heat conductor. How conduction works in solid. Conduction transfer heat without the material moving overall. It is the main method of heat transfers in solids. There are two mechanisms. Number one, particle vibration. When heated, atoms vibrate more. They collide with neighboring atoms, passing one energy until the whole solid reaches thermal equilibrium. Free electrons in metals. Metals contain many delocalized electrons which move freely and transfer energy rapidly, making metals excellent conductors. Conduction in liquid and gases. Liquid and gases are poor conductors because their particles are farther apart and do not pass on vibration efficiently. This is way this is why air and water are often used as insulating layer like in double glazed windows. Let's talk about convection now. What convection is? Convection is heat transfer through liquid and gaseous fluids. It does not occur in solid. Warm fluid moves and replaced by cooler fluid, forming a continuous cycle called a convection current. Density changes in convection. When fluid is heated, example air near a radiator, particles gain energy and spread out. The fluid becomes less dense and rises. Cooler, denser fluid moves in to replace it. The rising fluid cools again, becomes denser, and sinks. When fluid is cooled, example near an AC unit high on a wall, particles lose energy and come closer together. The fluid becomes denser and sinks. Warmer fluid rises to take its place. This again creates a convection current. Demonstration of convection in water. Put a few crystals of potassium permanganate, purple dye, in a beaker of water. Gently heat the water near the crystal. Warm colored water rises and moves across the surface. It cools and sinks, making the motion of the convection current visible. Let's discuss radiation, thermal radiation. What thermal radiation is? All objects emit infrared radiations. Hotter objects emit more radiations. Radiations can travel through a vacuum because it does not need particles. This is how heat from the sun reaches Earth. Effect of surface color and texture. So we have different surface types here. They're absorbing infrared rays and they're emitting infrared rays. If the surface is black and dull, absorbing IR will be very good and emitting also will be very good. For dark matte, absorbing and emitting IR both are very good. For white surface, absorbing and emitting IR both are very poor. For shiny surface, absorbing IR very poor, it reflects, and emitting also very poor, it reflects. Surface properties affects how well object absorb or emit radiation. Dark, black, dull surfaces absorb and emit radiation efficiently. Shiny surfaces reflect radiation, so they absorb and emit little. Let's talk about thermal equilibrium. An object heats up when it absorbs more energy than it emits and cools down when it emits more than it absorbs. Eventually, it reaches thermal equilibrium where rate of energy absorbed is equals to rate of energy emitted. At this point, its temperature becomes constant. The greenhouse effect. Why Earth stays warm. Without an atmosphere, Earth's surface would fall to around minus 180 degrees centigrade at night. The atmosphere helps keep heat in. How the greenhouse effect works. The sun sends radiation to Earth. Earth's surface absorbs this and remits infrared radiation. Greenhouse gases, carbon dioxide, methane, water vapor absorb and re emit some of this infrared radiations. Instead of escaping to space, some energy is redirected back to Earth, warming the planet. When greenhouse gas level increase, more heat is trapped, so Earth's temperature rises further. Investigation of infrared radiation. Aim to study how surface color affects the rate of heat lost by radiation. Variables, independent variable, surface color, black, gray, white, silver. Dependent variable is temperature over time. Controlled variables are size of container, water volume, starting temperature, time intervals. Equipment: 4 identical flasks painted black, gray, white, and silver, thermometers, stopwatch, kettle, and heat proof mat. Method: fill each flask with same amount of hot water at the same starting temperature. Record the temperature of each flask at regular intervals every 30 seconds. Analysis: all flasks lose heat by conduction, convection, and radiation. Conduction and convection should be similar in all flasks. The difference in cooling is due to radiation. A graph of temperature versus time shows black flask cool fastest, best emitter. Shiny silver flask cools slowest, poor emitter. Safety. Handle boiling water carefully. Wear eye protection if necessary. Keep water away from electrical equipment. Treat burns by running cold water over them. Make sure equipment is stable and not near the edge of the table. Consequences of thermal energy transfer. Conduction in everyday life. Useful conductors. Metal pans heat food quickly. Radiators transfer heat from hot water to air. Useful insulators. Plastic or wood handles on pans protects hand. Double glazed windows and insulation reduce heat loss. Convection in everyday life. Radiators heat nearby air which rises, setting up convection currents and warming the whole room. Hot drinks produce rising steam as warm air above the drink rises. Mixed heat transfers. Hot drink in a cup. Conduction from liquid to cup and to the table. Convection, warm air above rises. Radiation, heat emitted in all directions from the cup surface. Wood or coal fire. Strong heat radiation from the flames. Heated air rises, circulating warmth through convection. Car radiator coolant absorbs heat from engine by conduction. Radiator gives off heat by radiation and convection. Coolant returns to the engine once cooled. With this, we have finished our chapter.